pad oxide, pad nitride, and then you put your polysilicon on top. Okay. The purpose of this polysilicon is it acts. Yeah.
So how do you define the lateral dimensions of the wafer, today's wafer?
No, we'll okay. Try to understand the process now. The software-related issues we'll talk about later, right? Because there's a lot of steps. I want to finish it, and then we can discuss the software issues. But if any questions with respect to the process, you can ask. So yeah, so it's silicon, pad oxide, nitride, and then there's polysilicon, right? But this polysilicon is a mandrel. It's going to act as basically the mold for creating your fins, okay? And so the next step is, you need to define your polysilicon mandrel, right? So for that, you have to pattern this. So you need a tri-layer resist, right? So you need the ODL. You remember the optical polarization layers, then anti-reflection coating, and then a resist, right? And then on top of this, you basically do your lithography, right? This is the first mask for defining your mandrel, right? So you use a mask here, you pattern this resist, and then what you do, you use this resist to pattern basically your different layers, right? So first you pattern your psi arc, and then you use your psi arc to pattern your ODL, your planarization, right? So remember, when you do this patterning, you do one step at a time. So you use one to pattern the other, and the other, and the other, and so on, right? So that's what's done here. And then finally, you see the pattern is transferred to the poly, right? So this poly is now the mandrel, okay?
Wait, sorry, can you go back one and then flip this again?
Yeah, I've just patterned this, that's all. I've just used basically a 3 sidewall spacer. So remember how you create the sidewall spacers? First you do a CVD. Yeah.
I remember you
First deposit conformally and oxide, and then you etch vertically down, and what happens is the sides don't etch, right? So as much. So that you end up with this kind of sidewall spacer here. And then after this, what you do, you basically remove, okay, now this is important, right? So does everyone remember the concept of cut mask that we did when we talked about in class, right? So when you define this poly, remember this is like on a wafer. So when you actually define this poly, right? So when I actually pattern this polysilicon, yeah, it has some dimension here also, right? Although I showed only the region here, I showed only this region. But at some location somewhere here, it has an end, right? So when I create the sidewall space is located all around, right? But I want my fins only here and here. I don't want my fins here, right? So you have to open up a mask and remove the oxide, the sidewall spacer here, so that you don't have a fin at that region. Yeah.
Are we supposed to actually do this?
So you put resist and you cut this region, right? And in this region you have opened up over here, and you're going to now remove the sidewall spacer. Correct? And so now you have only sidewall spacer here and here, and some region here was removed where you didn't want it anymore. Correct? And then now you remove the polysilicon, right? So now you see here you are left with these two freestanding sidewall spacers, and some region of it has been cut. Okay? Now exactly why it's cut here is just to show you that how to do it, but it just you just want it removed at the region where you don't want to fit. Okay? It can be at any region, doesn't matter. How do you have this oxide sidewall spacer as freestanding, right? And now what you do, you now use this oxide sidewall spacer as now the hard mask to pattern the nitride and the pad oxide, and then you use this to then act as the mask to etch down the fin, right? So now you have a silicon fin that you see, there are 2 fins here, right? And what's going to happen is this fin here is going to be actually your NMOS, and this fin here is actually going to be a PMOS. Okay. Yeah.
That was like 3 to 4 etch steps that you just went over, right? We did the nitride, pad oxide, and the silicon.
Yeah. Yeah. There will be 3 different etches.
Those are 3 different etches.
Yeah. Yeah. Because oxide will be 1 etch, nitride will be 1 etch, then again silicon will be another etch. Yeah. So now you have etched down, and you created, and this fin is going to be for an NMOS device. That fin is going to be for a PMOS device. Okay. Yeah. So it creates this. And if you see here, that's basically a different way using polysilicon itself to dope the silicon. Okay. So remember, right, in a transistor, in the case of the NMOS, yeah. So remember that in the case of the NMOS, right? This was the NMOS. So you have basically the source and drains would be N-type, so it would be N plus, N minus, N minus, N plus. And this, the well itself, right? So this is called the well, the region of the body. This will be P-type, right? And then you have oxide, and then you have some metal, right? So this is the structure for your NMOS, correct? And the PMOS would be opposite to this. So PMOS would have P plus, P minus, and the body would be P-type, right? Sorry, N-type. So let me just write that so it doesn't create confusion. For the PMOS, it will be exactly opposite. P minus. So basically you want to create these, so now you have a fin, right? Remember, in the FinFET case, this body is actually the fin itself, right? So you need to uniformly dope the fin to the doping of the body, right? So this body is P-type here, which means for the N fin, so the NMOS fin has to be P-type dope, and the PMOS fin has to be N-type dope, correct? So how do you do that? So I'm actually going to do that with polysilicon, with dope polysilicon, I'm going to dope the fin, okay? And how you do that is what you can do is, like, you say you have silicon, right? And you want to dope the silicon, say N-type. What you can do is you can actually deposit on top of the silicon. So usually there will be some layer here, which is basically called as a diffusion barrier, which is usually made with some kind of a thin layer of oxide, okay? And what it does, that's to control the diffusion. And then you can put N plus poly or some highly doped polysilicon. And what happens is when you anneal this, the N dopants actually migrate into the silicon, okay? And they end up creating a well, which is N-type. Yeah. And then you can remove the poly. Okay, so that's one way you can. This is using diffusion to dope the silicon, but you can also use ion implantation to dope the silicon. Okay, so that's why I'm saying this is one way to do it. Okay, so what I need to do is I need to create a P well for the NMOS and an N well for the PMOS, right? So what I'm going to do is first I'm going to deposit. So this region is actually this diffusion barrier over here. Diffusion control barrier. So that's to control the amount of diffusion. And then I first deposited a basically I've deposited a P-doped polysilicon, right? And this P-doped polysilicon, remember that NMOS is the one that has a P body, right? So I need to have this only on the NMOS and I need to remove it from the PMOS, right? So that's what I'm going to do in the next step, is I'm going to basically pattern, so I put a resist, pattern the resist, and then what I'm doing is I'm etching the polysilicon from the PMOS side, right? So now I have this P poly sitting here and no polysilicon over here, right? Then after this, what I'm going to do is I'm going to deposit another polysilicon that's covering everything, but this is going to be N polysilicon, right? So now you have N polysilicon on the PMOS and P polysilicon on the NMOS, correct? There is N polysilicon on top of this P polysilicon, but that's far away from the silicon surface, so you don't really care about it. I knew you would ask that question. Yeah. So basically, you know, the P fin, right, is touching the N polysilicon, and the N fin is touching the P polysilicon. And so now when you anneal this, they're going to basically diffuse into it, and they're going to dope the fins, right?
They diffuse at the same time.
Yeah, because I'm annealing it together.
But the mobility would be different, right?
What do you mean mobility is different? If the mobility is different, I just dope these polys differently. Yeah. So also, you know, in some cases, right, you don't want these nitrides and oxides to also be filled with dopants. You don't want to make this conductor. So what you do is you also etch away the polysilicon on the top, the tips of this, and so you have polysilicon only on the sides. Okay. So that you can do with the same kind of etch you use to create a sidewall spacer. If you do that, you end up etching the poly so that they are only located at the sides of the fin. Okay. And then now when you do the drive-in, right, the thermal anneal, so this becomes doped P-type and this fin becomes doped N-type. Okay. So everyone understood up to this point, right?
So just so I'm still on track, we have had 3 masks so far, right?
I didn't keep count of them, but yeah, I'm taking your word for it. Yeah. So there's also alternate, yeah.
Just for clarity,
Fill all this space with oxide. That's your trench isolation, right? So what you do is you do this CVD deposition, PCVD of this high density plasma oxide. So usually when it says HDP, so there are so many different kinds of oxides you see. Okay, there's TEOS, then there is like LPCVD oxide, and there's HDP oxide. So HDP means high density plasma oxide. So HDP oxides are typically very dense. They don't have as many. You know, how dense an oxide is determined by, like, you know, usually oxide is SiO2, right? But usually it's not SiO2, it's SiOX, and can have some oxide vacancies in it, right? So the HDP oxide is one that's almost like SiO2. So it's like very dense oxide, it's a good quality oxide. But actually when you go higher and higher, when you go to a metal 1 and metal 2 and stuff like that, you actually use a poorer oxide, okay? Because it actually helps with your dielectric constant. Because the good oxide actually has a higher dielectric constant than the more porous oxide. So this is a high density plasma oxide, it's a HDP oxide, and now you need to like fill everything in, right? So that's where you do the CMP. And the CMP obviously stops on the nitride we had in the beginning, right? So, and then you also have some leaching here. And then now what you need to do, you need to remove these hard masks, right? You don't want this nitride oxide. So what you do a little recess etch of this HDP oxide, and then you basically, and this step is usually called as deglazing, and then what you do is you wet etch the nitride, okay? Yeah?
Before we move on, why did you deposit so much height of oxide?
So much height of oxide.
There's like 3 fins of height of oxide.
Why is this oxide is over here?
No, the HTP white oxide.
No, that's because, see, the thing is, it's like, it's just to show. It doesn't really matter. I could have done till here also.
Oh, doesn't matter.
Yeah. Don't worry about how much I use in the dimensions.
The numbers don't matter.
Yeah, it's just the process is what. Yeah.
A similar question. Why do you make this so tall?
Which the fin?
The fin is the top region of this whole kind of tower.
So the part has the silicon now exposed on the top, and all the offset around it has gone. So this becomes the fin that's actually going to be used for now making your transistor. Correct. Yeah. Okay. So yeah. So next, so Narendra. So 40 minutes is up, so will it automatically stop, or will it tell you it stopped?
No, it will stop.
Okay,
Well, actually zoom in it.
Huh?
40 minutes if there is no.
Okay, then let's just continue. Yeah.
No, it will end, right? You won't get the recording.
No, but it'll tell me the recording stopped, right?
I'm recording.
Huh?
Nice.
I'm recording. I mean,
Yeah. So So now you made the fins. And now the next step is how to actually make your gates, right? So now you have the actual region that conducts the current. And now you actually want to create a gate on top of this, right? That's perpendicular to the channel, right? So how do you make that? So far, this is what we've done. So if you look at the typical cross section at this stage of the process, so it looks something like this, right? Yeah, so next, you put some, remember always when you have silicon exposed, right, you never want silicon to be exposed, okay, it's not a good idea. So you always protect it with some barrier. So in this case, it's some oxide, some ALD oxide barrier. And then now that you have this, then what you do, now you're going to create your actual replacement gate process, right? So I hope you guys, so to do this, right, so the first polysilicon you used was the mandrel to create the fins. The second polysilicon you're going to use is also not going to be used eventually. It's going to be replaced with metal, right? So the replacement gate process, if you remember, is you use the That was the one I just used. So, the replacement gate process is basically, you first have poly, and then you create a shallow implant, and then you made, your silo spacer, then you made the deep implant, right? And then once you made this structure, right, you also need to add strain engineering also, we'll talk about that. But then in the replacement process, what you do is after you've done everything, you remove this polysilicon, right? So you have this removed, and then what you do is you fill this up with metal, right? You first deposit some high K dielectric here, and then you fill this up with metal, right? So the polysilicon is finally removed, right? So we're going to do that over here.
So before that, you should do another alignment, right? To deposit the metal right at the place.
No, this is also self-aligned.
Okay. So
Yeah.
we will deposit metal everywhere.
Oh, you mean no? When you define your first gate, right? This polysilicon gate. To define the polysilicon gate, yes, there's a litho step. But then to do replacement metal, there's no litho step because the replacement metal is just going where the polysilicon was originally defined, right?
How?
Yeah, talk about that. What you will do is like, say this was polysilicon first, right? So what you do is you kind of fill some kind of oxide and then you CMP down. So the oxide is like over here like this. Then you etch away your polysilicon and then you sputter like you do an ALD hafnia and then metal and then you CMP down.
Okay.
And then it's filled only here, right? And then everywhere else goes away. But you don't need a mask to do that because it's just defined in the place where your polysilicon was originally present, right? So that's the replacement gate. Yeah. So yeah, so now this polysilicon is for that process. Polysilicon and we planarize it. So we do a CMP, but this CMP does not need a polystop. Okay, it's a reference CMP, which means you CMP for a certain period of time till it gives you some thickness, and then you stop. And the way you do this in practice is you do CMP for different times, and you do a DOE, and you find out which gives you the right thickness you want. ODL, SIR, and resist. And now what you do is you expose the mask and you pattern this, and then now you etch all the way down, and now you transfer the pattern of the gates, right? So of the gates to this planarization layer, and then now you use this to pattern your polysilicon.
Sorry, what's the material of the gate?
Poly.
That's poly.
Huh?
The red is the poly, right? What is that, like grayish?
That's the ODL. That's the optical. Oh, sorry. No, that's the nitride. That's the nitride.
Green on top?
That's the oxide. This nitride is very important actually because we need it for the polystop when we do the replacement method, right? Yeah, and so now the next step I show it's an optional step which is usually done because sometimes what happens is in this step you want to create like a uniform mask, and then in the next step you want to cut out the gates at the region where you don't want the gates. The same way I showed for the fins, right? So I first created the fins, and then before I created the fins, I first created the sidewall spacer mask for the fin, and then I cut out those in regions I don't want, right? The same thing is also done for the gates also. So first you define your gates, the hard mask for the gates, but before actually etching the gates down, what you do is you have another cut mask to cut the gates at certain regions you don't want them. Okay, so here is an example of a cut mask for the gates. So again you do a 3-step resist process. So this is a planarization layer, SIR, resist, and this is a cut mask for cutting the gates, right? So you pattern this, and then you basically transfer the pattern to the ODL, and then you etched this nitride. So now you have cut the gate at certain regions, right? And so now, once the gate is cut, and then you have, this is your gate hard mask, right? So you have the nitride has been patterned, and the gate over there has been cut. And now you just transfer this pattern onto the polysilicon. So you just use a silicon etch, so polysilicon etch, and then now you've etched down all the way down. And now these are your polysilicon gates, right? With the nitride on top. Yeah. Next, what you have to do is, so this step is going to get a little complicated, so just follow along. What you're going to do is, you have to create the same way that in your planar MOSFET, right? So remember in your planar MOSFET, what you actually do is, once you created your also, yeah, one more thing I wanted to say is, there is also an implant step for creating a lightly doped grain region that I've not shown here, okay? So that part you have to kind of do it yourself because you need to calculate how much doping is for the lightly doped grain region. But remember that how you create the strain engineering for the bulk MOS, right? So first what you do is you create a lightly doped region, and then what you do is you kind of create the sidewall spacer, and then you etch the silicon down like this, but you do basically a wet etch. So you do crystal etch, and then you epitaxially grow your silicon germanium, something like this, right? And the silicon germanium in situ dope. So it's in situ dope to, like, you know, if this is a NMOS, this is in situ dope N plus, right? And this will be N minus. So this, and what happens is this, sorry, if it's, this will be silicon carbide for the NMOS. And so what this is going to do is it's going to basically create a tensile stress on the transistor, right? And on the channel, and that's what's going to create your enhancement in the electron movement. Yeah.
How do you do the sidewall spacer over the fin? Because if you're doing an
Oh, no, we're not doing it over the fin. Remember, that's the slightly confusing thing here. In this case, the fin is going in one direction, the gate is going in the other. So what you do is now you need to create your lightly doped region. So that's why first, that step alone is not shown here, but you basically create this mask on top. You open up first the NMOS region, and then you do a lightly doped N region, and then you close the NMOS region, open the PMOS region, and you create a lightly doped P region, right? And so now what you need to do, you need to do this step where you etch the silicon down, and then you epitaxially grow your, yeah.
I'm having some trouble like trying to understand, like, what do you mean, like, where would the lightly doped region be? Like, is it around the whole fin or just like that?
No, so in this case, right, so this is the fin. This is the fin, right? So your gate is going to go around it like this, right? So it's going to go like this, and then back. Right?
Oh,
No, the silicon germanium is the heavy dope. See, it's in situ dope.
Oh, okay.
Yeah.
Does in pseudo dope mean that you grow it and it's doped?
Great. And so these regions are going to be now the silicon germanium, and then you know, if I was to draw, right, if I was to draw the same thing here over here, this would be like this, it would go like this. You understand? In that way, right? And so this will be lightly doped region, and then this whole piece will be replaced with silicon germanium. And that's your N plus. You put the nitride, and then you have a mask because you want to open one side, because one side you want silicon germanium, the other side you want silicon carbide, correct? Remember, this was the NMOS fin, and the PMOS fin is sitting in the back side, right? So the PMOS fin is going to be silicon germanium, the NMOS fin is going to be silicon carbide.
So what was the reason that you cut the gate? Because for example, for invert.
No, it's an option.
Okay.
I just want to show that it's an option. You don't have to cut the gate. It's an option, because just like how you can first create a fin and then you cut the fin where you don't want, right? Similarly, because it's mentioned in your PDF document, you have cut mask for the fin, you have cut mask for the gate also. So I want to explain what the cut mask is for. That's why it's yeah.
So I got a little lost. We did the oxide depth.
But on the other side, I'm growing silicon germanium. So I'm opening up using the mask, I'm etching down the silicon and growing silicon germanium. But you can see for the silicon carbide actually. So now again, I'm covering with nitride. Remember what I mentioned, right? So now I'm going to open the silicon carbide region. So this one you can see. So again, I put resist, pattern the resist, right? And then what I'm going to do is I've etched the nitride all the way down to expose the silicon on top of the fin. And then what I'm going to do, I'm going to crystal etch the fin, right? So that's what I've done here. So I've crystal etched the fin down, you see here. And then now I'm going to epitaxially grow the silicon carbide, right? So you see here the silicon carbide is growing. So I hope you understand three-dimensionally what's happening here, right? This is the gate, and the silicon carbide is actually compressed, the distance is, you know, pulling it apart here.
Why do we not see that kind of hole on the germanium side?
Because it's hidden behind this. If you rotate it, you can see it. Trust me on that. I'm not hiding it from you. It's there. It's just hidden. And yeah, so yeah, basically, just understand what I'm trying to say is that, you know, the fin is being pulled apart in this direction, right?
Yeah.
This is the channel direction, and the gate is wrapping around it this way.
Why are there two gates?
Huh? Where is the second? What do you mean 2 gates? Forget that. That's just to show the pattern. This is not an inverter. This is just a pattern. I mean, if I showed everything, then there's no project, right?
I'm okay with that. Yeah.
Yeah. So then, yeah. So everyone understands here, right? So I etch the nitride, open up the source drain regions, then wet etch the silicon, crystal etch, and then epitaxially grow the silicon carbides. Yeah.
Does it matter how much we?
Why are you shaking your head?
I'm being honest.
Well, you can follow along the video, you can ask me later. Which part you don't understand? Yeah, but I hope everyone at least understands, somewhat how to do it. Yeah. Okay, so next what you do is, you gotta, so this completes the front end of it. Okay. Now is the middle of line, how do you create contacts to the source drain and gates, right? So again, there's a lot of, actually it's not done. I haven't done the replacement metal. So let's quickly finish since we don't have much time. But so now I've created the source, drain, and the gate. So now remember there's polysilicon here, right? I need to replace this with basically a metal, right? Why you need to do that? Because I still haven't put my high K dielectric, right? Everything here is still like some oxide nitride, right? And once you put your high K dielectric, remember why you need a metal is because once you have your high K dielectric, you no longer can put polysilicon. Because polysilicon is a high temperature process. And the moment you do a high temperature process, when you put a high K, it's going to damage the high K. So when you have high K, it's always going to be, the next step is always going to be temperature limited. So it's always going to be low temperature process, right?
Everything after the high K is low.
Yeah, that's why I use a metal, because metal can be deposited using CVD. CVD is a low temperature process. Sorry, PVD, yeah, sputter. Yeah. So now what do you do? Now you do the replacement process, right? Remember, I was explaining to you, like, once you had this polysilicon and you had, your silicon germanium here. So what you're going to do now is move, and then now you have this hole that is left, right? And now you can fill this hole with your high K dielectric and your metal K, right? But here's where it gets a little complicated because you need to have different work function metals for the PMOS as well as the NMOS. Okay, so they're going to be different kind of, and we'll talk a little bit about that if we have time. But your NMOS is going to have a completely different metal for the gate, and the PMOS is going to have a different metal, depending on work function, right? So now, basically now you open up this, and now you need to fill it with high K, right? So you do an atomic layer deposition of high K dielectric, so aluminum oxide, hafnium oxide, so that basically covers everything. And then now, first you need to create the metal for the PMOS. Then you're going to create the metal for the NMOS, right? So remember, the PMOS is here, the NMOS is, sorry, this is the NMOS and the PMOS is here, right? So first I'm going to create the gate for the PMOS, right? So the gate metal in this case is a combination of titanium nitride and tantalum nitride, and that really depends on what kind of work function is needed for the PMOS versus the NMOS. So first you sputter tinitride, tantalum nitride, and then remember that this metal covers everywhere, but you need to make sure that this P metal is only there for the PMOS and not there for the NMOS, right? So again, you need to remove it, right? So now you again do a mask, you put a mask here, and then you etch away the P metal, so that there's no P metal on the NMOS, right? And then you remove the mask, and then you sputter again, but this is aluminum, which is for the NMOS, so this is N metal, right? So now you have P metal on the PMOS and N metal on the NMOS, right? And yeah.
Too quick, can we like slow down?
Yeah.
Okay, tinitride.
I'm gonna go here. It's easier to explain later.
No, I understand this.
So first the hafnia. This is the P metal.
Yes.
But I don't want the P metal on the NMOS region,
Yeah.
right? So I remove it, right? So I mask it, and then I etch the P metal here, so it's gone.
How do you etch?
Just wet etch or something, dry etch or wet etch. But it stops on hafnia. But always, when you etch, it's one versus the other, right? So this etch can etch a metal, but it cannot etch an oxide. So it stops on the hafnia, right? And then now you see the P metal is only on the PMOS. There's nothing on the NMOS. But now when you sputter aluminum, which is for the NMOS, so aluminum now sets the work function of the NMOS, right? And the PMOS has its own work function metal. It doesn't really matter that the N metal is sitting on the P metal because it's only the metal that's nearest to the gate oxide that determines the work function. So this metal, this other metal which is sitting on top of the P metal, the N metal on top of the P metal, is just a conductor. It doesn't really contribute to the work function, Okay? It's only the metal that's in contact with the hafnia that matters. So that's why it's okay that this end metal is now, this way. It's okay that this end metal is sitting on top of the beam, right? And now you have defined basically your hafnia, you have defined your actual metals that defines the work function for the PMOS and NMOS. And now you still have this empty space which you need to fill with some conductor, right? So that's typically tungsten is used for that. So you deposit, you sputter tungsten, so it fills everything. And then to finally fill the holes, you do a CMP. And the CMP is going to stop on the oxide. It's a timed CMP again, okay? So it doesn't stop on a nitride rock, on a nitride, but you time it so that it just gives you the corresponding gate height that you want.
How do you know?
So now I did the CMP, and then after that, you usually cap it with some nitride. Okay, so you deposit some nitride, and then you cap the surface with nitride. Usually, this is an additional step that is used. You always don't want to expose the gate to the elements, so you usually cap it with nitride.
How did you CMP the tungsten down?
Correct. So now to create contact, it's just the same as the previous case I mentioned earlier. Is once you have this, once you have the gate, this is a replacement gate, right? So this is our metal. Now what you do is you just fill it with some kind of oxide, and then you planarize the surface, and then you etch down contacts all the way down, and then you fill it with tinitrate tungsten, right? So that's your tungsten contact. So that's what I'm going to do here. So, yeah.
Before that, what is that like darker light blue layer that we put after the cap, after the neck?
This is just some oxide.
Some oxide.
Yeah. Rule will be there in the design. Yeah, and so now you create a contact. So you put again 3-layer resist, you pattern. So this is the contact with the source drain. This is the contact with the gate, and then you etch down all the way till the basically the metal, and that's what's shown here on the right. And then what you do, you fill it with, you basically sputter tinitride tungsten. So tinitride is usually a barrier. You always don't want to put metal directly in contact with silicon. So you put some tinitride and then tungsten, and then you CMP it down, right? Again, this is also a reference CMP. So the CMP, where you stop, depends on how long you do the CMP, and you have to optimize that. And then now and this completes your complete front end of line and middle of line, right? So now you've created your tungsten contacts to the FinFET transistors with the replacement.
You said this is a timed CNC?
Yeah.
But you are showing it polished stuff.
No, there is no polished stuff here. Everything here is oxide. No, there's no polished stuff. See, this is oxide, this is tungsten,
Yeah.
this is tinitride. There's no nitride here.
Yeah, but it's not that outside.
No, there's no stop. You basically put enough height, so you put enough height of oxide, enough height of tungsten, and then you CMP all the way down and you stop.
You also remove it.
No, tinitride is not a polished stuff. Tinitride is just a barrier.
Remove it, right?
Yeah, you remove it. That's what I'm saying.
Where did I remove
I
it?
mean, after you CMP.
Yeah.
Oh, but that's timed.
That's
It's not
timed.
stopping on the oxide.
Okay. So you're over.
Yeah, you
Oh, I
polishing
see.
till it goes away. You understand what I'm saying? How this looks like once you made everything kind of transparent is this is your your actual source drain. This was the contacts, and this is your replacement metal gate, right? Which is going, and you can see here how this is a channel, and the gate is actually going like this one. And this is the entire fin structure, right?
So the CD or silicon carbide is not only your material for strength, it's also your source and drain.
It's also your
Source and drain.
I haven't done silicylation. You have to do silicylation on the source of drain, right? That's one I haven't shown. The other one is a lightly doped, but that's just an implant that I use. So that's two things I haven't shown you yet.
How many steps do you have?
I didn't count. After this, the job is not done, right? Because you have an inverter, so that's not that difficult. You just put oxide, you create a pattern, then you basically put a seed layer, electroplate copper, CFP, and then you create metal 1, then you create dual damascene, then you create metal 2, right? And that completes your thing. So on top of this is just a front end, middle end, and then on top you have 2 levels of copper that defines your back end, right? And then you have the full interconnected front. A 40 nanometer cross section. So you can see here, these are the fins, right? You see they're standing up here. And you have around 13 levels of metallization to go all the way to the top of the chip. So And if you notice here, right, so, yeah, so basically these are the vias and these are the actual metals that are, created using. And the reason why these metals are, you see they are very flat on the surface is because there's a CMT step here. That's why they are like flat. You build on top of it. The offset capacitance per unit area, okay? And over here you see this Na, right? So depending on how much doping you have in your body, as well as the work function difference, you can calculate what the threshold voltage of the transistor is, right? In a FinFET it's slightly complicated because in your case, right, if you assume that the fin is not very narrow, then you can assume that you can assume that there's not much variation in the potential when you go in the orthonormal direction. Okay, so this vector is normal to the fin, right? Normal to the surface here. Right? So this is the gate, this is the actual silicon, and this is your inversion layer shown here, right? So if the potential is not really affected in the cross section and only depends on the normal direction, right? Then you can use the same formula I showed before, okay? Because you're just calculating in the normal direction. But if your fin was very narrow, right? Then the way usually people do it is you need to actually calculate. You need to solve Poisson's equation in this cross section, calculate what your potential distribution is, and then from that you need to calculate what is the total charge in this and divide that by Cox to calculate your threshold voltage, right? And this can get very, very complicated. So here's an example of how it is done from paper where they solve the three-dimensional Poisson's equation in the cross section, and so the charge. When you solve this, the charge calculation for the potential distribution gets very complicated. And so here you see this is the potential as a function of location.
That's an analytical solution.
Yeah, this is an analytical solution. But then I just want to show that how you would do this in the FinFET case. But then for our case, right, you assume that the FinFET is not that narrow, so you don't have to do this two-dimensional Poisson calculation. And you can assume that the potential only varies in the normal direction, so you can use this traditional bulk mass formula. Right? He's very happy. Yeah, so, and here's a summary of different kinds of metals. So depending on whether it's a PMOS or NMOS, when you use that formula, right, it turns out that only certain metals work to give you the correct threshold value for a PMOS versus an NMOS. And usually for all the possible metals, right, so you see for the PMOS, typically that's why we use kind of titanium or something like that. Yeah.
So here you're showing work function of metals, but when we do all the deposition, it's all of nitrides. Why do we do that? Why is it
Because that actually changes the work function slightly.
So we nitride every
See, the metallurgy, usually when you deposit these things, will typically be some kind of aluminum based thing. That's why you use Ti aluminum for the NMOS, right? But you use titanium for the PMOS, because that's what gives you the right work function. And usually, there's a lot of physics that goes into choosing the correct kind of metal and correct kind of alloy. And you use a lot of, that's why, when people usually design a transistor, there's a whole team that models this using some kind of CAD software to model how the potential is in the cross section, to calculate what the threshold voltage is. And then they choose the metal that gives you the right value of the threshold, right? And that usually involves some kind of alloying and different kinds of metals are used. Yeah.
So that's on my